In this module, you will learn to read the standard circuit diagrams of hydraulic systems and understand the functionality of those systems. The following learning objectives need to be achieved with this module. You should be able to justify the representation of hydraulic components as graphical symbols and differentiate them from other types of representations. You should be able to understand and apply the systematic design of graphical symbols and circuit diagrams. You should know the most important basic elements of graphical symbols. You should know the most commonly used symbols from all of the functional groups in a hydraulic system. You should be able to explain the functionality of a simple hydraulic system based on a standard circuit diagram. Graphical symbols are abstract representations of hydraulic components. When combined into a circuit diagram, they show the schematic representation of design and interconnections of a hydraulic system. In order to understand the design and functionality of a hydraulic system, we do not need to know what it looks like. The constructive details of the individual components are also not important. It suffices to represent which components are installed and how these are connected one with one another. With the aid of symbols, we can represent the design and functionality of a hydraulic system in a simple manner that is understandable to any hydraulics engineer. Symbols are essential for the planning, assembly, testing, operation, maintenance, troubleshooting, and documentation of a hydraulic system. Symbols illustrate the exclusive function of a component or device. Some symbols also show activation procedures. Symbols are not used to represent the construction of a device. It is important that the symbols used are uniform for understanding. Therefore, graphical symbols are subjected to International Standard DIN ISO 1219. Graphical symbols are generally composed of individual symbolic elements. DIN ISO 1219 defines the symbolic elements that may be combined into various symbols. This is very similar to a construction kit system. From a pool of symbolic elements, we can compose the symbol for a variable displacement pump, for example. Every graphical symbol consists of a basic symbol containing the most important information about the component or device. For example, a large circle stands for an energy converter, such as a pump or hydraulic motor. Components are more specifically defined, however, through the addition of one or more functional elements to the basic symbol. For example, a small solid triangle stands for a source of hydraulic energy, while its orientation shows the direction of flow. A circle with a small solid triangle pointing outwards has the following meaning: energy converter from which hydraulic fluid is pumped out. You are already familiar with this device. It's a hydraulic pump. The components are connected together by straight lines, which can cross or join together and may contain connections. The example shows a line connection. Mechanical components are required to perform drive or control functions. Example, shafts. Often, the type of actuation is also shown. The symbolic element for manual actuation is symbolized by a lever. Graphical symbols are made up of one or more of these symbolic elements. There are graphical symbols for all hydraulic components in the functional groups of a hydraulic system. Energy supply and processing, example, hydraulic pumps. Energy control and regulation, example, directional control valves. Energy conversion, example, hydraulic cylinders, as well as other accessories, example, pressure measuring instruments. The symbols for the various hydraulic components are combined together in a schematic diagram of the hydraulic system. These diagrams show which components are present in the system and how they are interconnected with each other. This allows the function of the system to be determined. Using a simple circuit diagram, we will now show the most important graphical symbols and explain their interactions in a hydraulic system. Let us now look at the hydraulic components in the functional group Energy Supply and Processing. Our example contains the following components: tank for hydraulic fluid, hydraulic pump, pressure relief valve, return line filter, cooler, fluid level indicator, and thermometer. Tank with hydraulic fluid is represented in its simplest form as an open rectangle. Tanks are generally closed in order to protect the hydraulic fluid from contamination and oxidization. We will therefore equip our tank with a cover. The hydraulic pump draws hydraulic fluid from the tank and delivers it into the hydraulic system. You already know that the large circle with the black triangle is the symbol for a hydraulic pump. The pump is driven by a shaft. To connect the shaft to the drive motor, a coupling is required. An arrow shows the direction of rotation of the shaft. The direction of rotation is only represented when necessary, for example, to ensure the correct connection to an electric motor. The pump requires working lines at inlet and outlet. A further line is shown, which feeds the leakage oil back into the hydraulic tank. Leakage or drain lines are represented with a dashed line. The diagonal arrow shows that the device is adjustable. With a hydraulic pump, this means that the flow rate delivered by the pump is variable. Such pumps are called variable displacement pumps. In order to protect the hydraulic systems from excessive pressure and overloading, the maximum allowable system pressure is limited using pressure relief valves. Pressure relief valves limit the pressure in a hydraulic system to a specific preset value. The graphical symbol for a pressure relief valve is based on the symbolic element for a valve, a square. The actuating device of the valve is a spring, which ensures that the valve remains closed in the rest position. The arrow symbol is used to represent adjustability. Spring tension is adjustable, and so therefore is the system pressure at which the valve opens. An angular dashed line is used to denote the pilot control within the pressure relief valve. Fluid in the pilot control line allows the system pressure to appear at the valve seat. In the event that the system pressure reaches the preset value, the pressure relief valve opens and the excess flow back into the tank. The direction of flow when the valve opens is represented by an arrow. The arrow is also used to show the path which the flow rate flows through the valve. Hence, it should actually lie between both the ports. Since the valve is closed in the rest position, the flow rate is blocked. This is represented in which the arrow lies on the edge of the square and in which the ports are not connected to each other. In general, graphical symbols always show components in their rest positions. The pressure relief valve is normally installed in the hydraulic circuit on the delivery side of the pump. Such line connections are normally represented with a dot. Once hydraulic systems are in operation, the entry of contaminants into the system is usually unavoidable. The hydraulic fluid carries the contaminants in the flow and transports them to the tank. In order to prevent contaminants from being drawn into the hydraulic pumps and re-entering the hydraulic system, a filter is generally installed in the fluid return line. Filters purify the returning hydraulic fluid and are therefore known as processing equipment. The basic symbol for processing equipment is a diamond shape. Since a filter works like a sieve, a diagonal dashed line is drawn into the diamond. Thus, the processing equipment is characterized as a filter. Pressure rise generates heat. Due to the pressure rise in the hydraulic system, as well as through heat absorption from hydraulic components, such as hydraulic motors, the hydraulic fluid is constantly heating up. In order to prevent the fluid from overheating, cooling devices are generally installed. Coolers, like filters, serve to process the hydraulic fluid, and therefore they are also known as processing equipment. The vertical line drawn through the center of the diamond represents the fluid flow path. It is not necessary to show the direction of the flow through a cooler. A line drawn perpendicular to the flow with two arrows pointing outwards symbolizes the dissipation of heat. Hydraulic fluid is generally monitored whilst it is in the tank. This is achieved with a fluid level indicator. Fluid levels must never be allowed to fall below the recommended levels for the tank. A fluid level indicator is a measuring device. The basic symbol for a measuring device is a medium-sized circle. The horizontal line within the circle symbolizes the level of the fluid. The float gauge floats on the surface of the fluid and therefore rising and falling together with the fluid level in the tank. The float gauge is represented in the symbol by a short vertical line. A fluid level indicator is normally a sight glass. We have already mentioned that hydraulic fluids constantly absorb heat during operation. This heat is normally removed from the fluid by a cooler. In order to monitor how much heat the fluid has absorbed, we need to know its temperature. This is done by installing a thermometer at the tank. Thermometers are measuring devices, and therefore the graphical symbol for a measuring device is once again used to denote them. A vertical line is drawn within the circle in order to show that the measuring device is, in this case, a thermometer. A black circle drawn in at the foot of the line portrays a mercury-filled glass bulb, and is therefore reminiscent of the very earliest thermometers. We can now schematically portray the energy supply and processing of a simple hydraulic system using the symbols we have learned now. A variable displacement hydraulic pump draws fluid from the tank and delivers it into a hydraulic system. The pump shaft is provided with a coupling for connection to the drive motor. The rotational direction of the drive shaft is shown. Leakage oil from the pump is fed through a separate hydraulic line back into the tank. The hydraulic pipeline is tapped on the delivery side of the pump, and an adjustable pressure relief valve is installed to control the flow. In the event that the system pressure reaches the preset value, the pressure relief valve opens. The excess flow rate supplied by the pump is then directed through the valve back into the tank. Hydraulic fluid is heated up when flowing through a hydraulic system and picks up any contaminants in the circuit and carries them away. A filter is normally installed to purify the fluid and a cooler to lower its operating temperature. The fluid temperature in the tank can be monitored using a thermometer. A sight glass allows the fluid level to be continuously monitored. We will now look at the functional group of energy control. The purpose of the components in this group is to match the hydraulic energy supplied with the exact requirements of the consumer. This task is carried out by using hydraulic control and regulating valves. Our example consists of the following components: the check valve, the directional control valve, and the flow control valve. We must ensure that at the output of the pump, flow is possible in one direction only. This is achieved by directing the flow through a valve that allows fluid to flow in only one direction. This type of valve is called a check valve or non-return valve. A check valve works like a ball sitting in a funnel. When the flow comes out of the funnel, the ball is pushed upwards and the valve is opened. When the flow comes from the other direction, the ball is forced against the opening in the funnel and effectively closes it. The flow is therefore blocked. This principle is represented in a graphical symbol. The symbol also indicates the direction in which the valve is closed. In order to control the flow, additional valves must be used. Valves used to start, stop, or change the direction of flow in hydraulic systems are known as directional control valves. You have already become familiar with the square as the functional symbol to represent a valve. The symbol for a directional control valve is made up of a number of squares. Each square in the symbol stands for a possible spool position. As you can see from the diagram, the directional control valve shown has 3 spool positions. the ports to directional control valves are also shown. In this example, there are 4 ports. The lines within the squares indicate the direction of flow within the respective spool position. Arrows indicate the possible flow direction. In the spool position shown, the direction of flow rate is from the pump fed back into the tank. In order to describe the switching properties of a valve, we need a designation of identifying the spool positions and ports. The 3 spool positions have been designated as A, 0, and B. Generally speaking, lowercase letters or numbers are used for spool positions. Ports, however, have uppercase letters. The pressure port is designated as P. This is the connection to the hydraulic pump. P stands for pressure. The return port is designated by the letter T. This is the connection to the reservoir, earlier called as tank. There are 2 working ports shown, designated as A and B. These are the ports to which the hydraulic load or energy converter will be attached. In spool position 0, the working ports of the directional control valve are closed. With the valve switched to this position, any flow supplied by the pump will be fed through port P and directed back into the tank. In spool position A, flow is directed in accordance with the crossed arrows. In other words, the flow is directed from port P to B and from port A to T. Directional control valves are designated in accordance with the number of ports and spool positions as follows. The first number indicates the number of usable ports. In our case, this is 4. The second number indicates the number of possible spool positions. In this example, there are 3. The symbol for a directional control valve also normally contains information about its actuation. For example, to fully understand the operation of a hydraulic circuit, it is important to know whether a solenoid valve is to be manually operated or automatically, as is the case when a cylinder is extended to its end position. Symbols denoting actuation are used to complement the respective spool position of the valve. In our example, these are solenoids. The diagonal slashes indicate that the solenoids are provided with only one coil, and therefore function only in one direction. The direction of the diagonal slash indicates the function direction of the solenoid. In our case, this means that the coil is actuated in the direction of the moving element. Springs ensure that the valve returns to its central, neutral position when there is no voltage applied to the solenoids. For a better understanding, let's see how a directional control valve works. When a voltage is applied to the left solenoid, the solenoid pushes the valve piston in the direction of the diagonal slash. The directional control valve is then switched to setting A. In this spool position, flow is directed from port P to B and from port A to T. If the voltage on the solenoid is removed, the piston is pushed back under spring action into spool position 0. When a voltage is applied to the right solenoid, the solenoid pushes the piston into spool position B. Now the flow is from P to A and from B to T. After the voltage has been removed, spring action returns the valve to spool position 0. This is the neutral position of the directional control valve. It should be noted that graphical symbols are generally represented in the neutral position of their respective components. A further requirement of the components of the energy control functional group is to regulate the amount of flow. Flow control valves are used for this purpose. Flow control valves, which effectively decrease pipe cross-sectional area and therefore throttle the rate of flow, are known as throttle valves. The symbol for a throttle valve has been chosen to illustrate this constriction in the flow rate. Throttle valves may be adjustable in order to regulate the flow to the required level. Therefore, the graphical symbol contains an arrow to denote adjustability. We can now use the components of the energy control functional group to extend our hydraulic system as follows. A check valve positioned at the supply output ensures that flow continues in one direction only. This prevents fluid from flowing out of the hydraulic system and into the pump after the pump has been switched off. A 4x3 directional control valve is installed to alter the direction of flow. In its neutral position, the valve directs the flow through pressure port P and back to the return line through port T. If the directional control valve is actuated by one of the two solenoids, it is switched either to position A or to position B. In spool position A, flow is directed from port P to B and from port A to T. In spool position B, flow is directed from P to A and from B to T. If no voltage is applied to either of the solenoids, the valve is not actuated. We refer to this as the neutral position. An adjustable throttle valve is used to limit the flow rate either to or from the consumers. We must now focus on the functional group energy conversion by consumer. They convert hydraulic energy into mechanical energy. This function is performed by the hydraulic cylinders or hydraulic motors. Our example contains just one of these components, the hydraulic cylinder. The main components of a hydraulic cylinder are the cylinder barrel, the cylinder cap enclosing one end of the cylinder barrel, the piston running inside the cylinder, the piston rod which supports the piston and transfers piston force, the cylinder end cover which encloses the other end of the cylinder barrel. The cylinder also requires ports for the supply and return of hydraulic fluid. When fluid is applied to the cylinder via the port on the cylinder cap, the piston is forced to extend. When fluid is applied via the port on the cylinder end cover, the piston is forced to retract. The hydraulic cylinder shown in the example is therefore referred to as double acting. To avoid piston impact at each end of the stroke, our cylinder has also been equipped with end position cushioning. These help to prevent shock damage to any expensive tool connected to the cylinder or to the cylinder components themselves. With the hydraulic cylinder connected as the consumer, we now have a complete hydraulic circuit. The functionality of that circuit will depend on the valve switching plan. A variable hydraulic pump supplies hydraulic fluid into the hydraulic system. A check valve prevents any hydraulic fluid from returning to the pump out of the hydraulic system. A solenoid valve is used to change the direction of flow. With the valve in its neutral position as shown, flow is directed back into the tank. With the valve in this position, no fluid is applied to the hydraulic cylinder, and its piston therefore remains stationary. There is no flow through the pressure ports on the cylinder. The piston is therefore unable to move even under the pressure of an external load. When the solenoid valve is switched to position B, the piston extends. Piston speed is regulated by the adjustable throttle valve. In the event that piston resistance approaches the maximum allowable pressure in the hydraulic system pressure, a pressure relief valve is actuated. Once opened, the pressure relief valve allows excess flow to return to the tank. When the solenoid valve is switched to position A, the piston retracts. Fluid then flows via the return port on the cylinder to working port A on the directional control valve. Flow is then directed through port T in the direction of the tank. Before the fluid returns to the tank, it is directed through filtration and cooling devices. In the tank, the fluid level and fluid temperature can be monitored using a sight glass and thermometer, respectively. In principle, our hydraulic circuit is already functional. In practice, however, a number of other components are necessary, with which we are still unfamiliar, and which cannot be classified in any of the three functional groups yet described. Components that cannot be classified in any of the three functional groups of a hydraulic system are called other accessories. Among these components are, for example, lines and line connections, hoses, union connectors, measuring and test equipment, and pressure accumulators. Since it would have been impossible to understand the interplay of hydraulic components without depicting the way in which hydraulic fluid flows within a circuit, we have already made reference to lines and line connections. We now need to look at another type of line connection, the flexible hose assembly, and a further hydraulic component, the pressure measuring instrument. You have already become familiar with lines and line connections. It is important to note that lines are only connected one with another when their connecting line junctions are clearly marked with a dot. Lines that cross each other without a dot are not connected one with the other. In that case, the lines are shown crossed purely for schematic purposes. It is not uncommon to note that certain sections in a hydraulic system have no fixed lines installed, that is, in mobile hydraulic applications. In the diagram, this is represented by the graphical symbol for flexible lines. Such lines must obviously be connected to the surrounding hydraulic system. The flexible line symbol, therefore, has two clearly marked connection points. At the input to the pressure relief valve, our hydraulic circuit will also be equipped with a pressure measuring instrument. In the schematic diagram, this component is represented by the symbol for a measuring instrument. An arrow, invariably pitched at 45 degrees west of north, is intended to denote the indicator of the pressure measuring instrument.